Now, what are you going to be learning in the class? Okay, so the class is CS201, so it is a core course in the CS program. So in that way, we basically design it primarily for that purpose, meaning that it's a core course and it's there to build a certain understanding on the part of the CS students to do data structures and algorithms. But of course, we welcome IS students. It's just that I need to note that there are some overlap between what you would have covered computational thinking. And I'm going to tell you a little bit more about what the differences are. And so you can decide for yourself whether this is a class that you're going to be interested in. Okay, so first, what is an algorithm? What are data structures? And why do we need to learn them? Okay, what is an algorithm? So this is a definition that we take from Wikipedia. Okay, an algorithm is a finite sequence of well-defined, computer implementable instructions, typically to solve a class of problems or to perform a computation. Okay, the basic thing here is that it's a sequence of well-defined instructions. It is a sequence, so you need to do it in a particular sequence. You cannot get it out of sequence. And it must be well-defined. Well-defined in the sense that it should be specified to such an extent that we can write a program that does that without any ambiguity. And that is what an algorithm is. And we're going to take a look at a simple example. Okay, so one of the problems that we did maybe back in primary school is something that is called GCD, right? Greatest common divisor. So somebody gives you two numbers and we ask the question of what is the largest possible number that can divide both of the inputs. So let's say if we give you 72 and 18, right? Now, a lot of you would be pretty good at math, right? Then you can say 72, 18, and you know immediately what is a GCD. Now, what is a GCD? It's 18, right? Because 72 is a multiple of 18, so 18 can divide both numbers. Now, except that when you're solving a much bigger problem, then you need to use a calculator. Now, the question is that what does your calculator need to do to get an answer? That means like if you were to open it up and look inside the calculator, what does it do to actually compute the outcome of the GCD? And it turns out that what the calculator has to do is what we call an algorithm. The calculator has to execute a certain instruction set to get the answer. And for the GCD, one possible algorithm is what we call the Euclid's algorithm. Now, this is the Euclid's algorithm. All right, so it is a series of instructions. Now, this is expressed in terms of a flow chart. And in the flow chart sense, right, you see any diamond. And the diamonds are basically the if, right, the conditions. So you have cases. You're going to have, okay. Okay, so you have the diamonds. The diamonds are the conditionals. So yes or no. And if yes, you go in one direction, no, you go to another direction. Now, the rectangles are the instructions that you need to execute, and they are usually atomic instruction. So a specific thing you do that is going to produce a particular outcome. Now, and this flow chart is expressing it in the following way. Basically, the termination condition is whether or not one of the numbers is 0. Now, that is a termination condition because if that happens, yes, then you go all the way to the end, and it's going to print the output, and then end, right? It terminates. Now, but if it doesn't go into the termination condition, then it will check whether or not one of the numbers is larger than the other one. And if that is the case, then we're going to subtract the smaller number from the larger number. Now, if you subtract a number from another number, the bigger number is going to get smaller, right? But it's going to keep on getting smaller until at a point of time, well, either any of them is going to go to 0 or they don't, right? Now, in this case, let's say in the first iteration, none of them is 0, but 72 is larger, so we subtract 72, we subtract 18 from 72, we get 54. Now, the input now is 54 and 18. So we're going to execute another iteration, we get 36 and 18. The third iteration, 18 and 18. And then the final iteration, you get one number, which is B, to be 0. Now, then the other number is the answer. Okay, so then in that case, then we now have the answer, and that is the GCD. Okay, now this is an algorithm. It has nothing to do with the programming language, right? Because we don't see any programming language here. All we see is just a flowchart. It's just a series of instructions, conditions, and so on. Which means that when we take a look at what an algorithm is, usually we don't talk about a specific programming language because an algorithm is the instruction itself. We should be able to execute it regardless of what the language is that we use to write that particular implementation. It has nothing to do with operating systems, so you can run it on a Mac, you can run it on a PC, you can run it on Linux, and if it is the same algorithm, it's going to produce the same answer to the same input. It is not specific to the computational power. I mean, so in this case, of course, if your computer is more powerful, you're gonna run this program faster. But that has nothing to do with the algorithm itself. It is a property of your computer. So because anyway, if you're comparing algorithms, then you can compare different algorithms on the same computer. Okay, so if it is nothing to do with all those things, then what does matter when we talk about an algorithm? And it turns out that two things matter. And the first thing is correctness. So what we mean by correctness is that this is an algorithm that is going to produce the right output given an input. If it is not correct, then by default, it's not an algorithm because in that case, right, it doesn't actually produce what you want to get. And the second thing is that it must be efficient. And efficiency here, it can be expressed in terms of both memory and time. And these are the two concepts that we will come back again and again. In fact, the whole course, I mean, until the end, we basically will talk about, is it efficient in space, is it efficient in time? And soon enough, we will figure out that these two concepts are somehow interrelated, that in most cases, they form a trade-off. You get space or you get time, but seldom do you get both of them at the same time, okay? So we will get to some examples soon in terms of doing that, okay? So what is a data structure then? And why do we talk about data structure and algorithms? Now, it turns out that data structure is a way to organize data. Organize them, manage them, store them. And the keyword there is that we want to have efficient access, right? So in this case, we need to access it efficiently. We need to modify it efficiently. And it turns out that the notion of data structure is closely connected to algorithms, exactly because both of them are dealing with solving problems. Now, when we ask you to solve a problem, frequently you need a piece of paper, right? Why do you need a piece of paper? Because you are keeping track of some intermediate outcome of that problem before you get to the final solution. If you do everything in your brain, I mean, depending on how much memory you have, right? I mean, probably you could. But we can always get a problem to be big enough that at some point you need an external or an outside source to do that. Okay? Okay, if I'm checking my phone, right, I'm not really checking my messages. I'm actually checking Teams, right? Because since anybody, whether they actually have that. Okay, all right. Okay, now what is an example of this type of data structure? Okay, so let's say here we give you two pieces of text. Now, this is actually the same piece of text. It's just that they are organized differently. So text one, we present the words in the sequence in which they naturally occur. And in that way, we can understand what the text is actually talking about. And if your purpose is to express a natural language sentence and you want to basically make sense of the meaning within the text, then you probably would keep track of the sequential nature of the words in the original text. Now, in the second text, we have the same set of words, but now we store it alphabetically. Now, if I just give you the alphabetical set, right, and then I ask you what it means, I mean, maybe you could, right, because you know what these words are and you're very familiar with them. But for any random text, we can't actually read them. So it means that the kind of problems that we are solving, depending on the way that we organize the data, is going to be different. If we ask you to find the occurrence of a word, let's say republic, right? This is much easier done on this text than this one, right? Why? Because if it's alphabetically ordered, then I have some expectation of where the word republic might appear. Well, it starts with R, so that means that it must be appearing somewhere where the R words are going to be. Now, that is going to allow us to solve a problem in a way that is going to be faster in terms of detecting the occurrence of a word. Now, but the cost of doing that is by first organizing the data in a different way than the way that it originally came with. So that's basically why we study data structures and algorithms together, because it turns out that algorithm depends on how you organize the data. And there is a big part of that, of how you solve the problem, that depends on the kind of organization of the data. We will try to see some examples of this in this class today. Okay, so when we talk about data structures, once in a while, we get this term, abstract data type. So what is abstract data type? Now, we will break down this particular phrase, right? But the most important word here is abstract. Now, when we talk about something in abstract, what it means is that we care not about the specific instantiation of it, but we care about the description of a concept. So when we talk about human, for example, right, there's an abstraction because they are different people. They are different individuals by a particular name and so on. But at the abstraction, humans can do certain things. And in that way, when we talk about data structures, right, we talk about abstract data type being the concept of it that describes what the object is, what it can do, what it cannot do. That is just the interface. So if you speak of it in the language of Java, for example, right, then this is like defining an interface to a class. It just defines what the class can or cannot do. It doesn't define how the class is going to do it. So that is basically the notion of abstraction. And it is important in computer science because a lot of times when we talk about different objects, we talk about them abstractly. And the reasons why we want to do so in an abstract way is so that we can increase the applicability. So for example, I may be using a particular algorithm to solve the problem of finding the fastest route to go from one city to another city. But here the city is just an abstraction, because I could use the same algorithm, for example, to design a way to draw the electrical wires on a circuit board that minimizes the amount of materials that I'm going to use. It's going to be the same algorithm. It's just that we talk about different specific objects in the two cases. Okay. So what are the advantages of this notion of abstraction? Okay, one, of course, is encapsulation. What it means is that we're going to hide the actual implementation from the clients. So the clients only needs to know the interface. They don't need to know the way that it's being implemented. Okay, localization, it means that the same data type is going to be used again and again in multiple different clients. And we want to localize implementation just to one place. So if you have a code, for example, that does something specific, for example, like sorting, right? You don't want this code to be all over the place, being copied and pasted in all the possible ways that it has been used, because if there is a bug in that code, then you have to go to all the different places to fix them. So in localizing it, then we avoid that problem, because then I just need to fix one place, and it's going to fix all its instances. And of course, the last one is flexibility. A big part of the kind of discussions that we have in class is going to be about, I want to solve a particular problem. What are the different ways in which I can solve them? And usually, for a given problem, I have many algorithms to solve them. And then we need to get into discussion of which one is better. And when we get into discussion of which one is better, then we have to define what better is and what our objectives are. And therefore, there are usually more than one way to solve a problem. And that's basically the beauty of algorithms, that you can see there are many different ways and patterns to finally solving the problem. Okay, just a quick example, right? And then after that, we're going to go into the breakdown of the different things we're going to do over the term. Okay, and a simple example is a list. And we call it an abstract data type because a list is just a sequence. It's a sequence of something. And usually what it means is that it's a sequence of the same object, because you keep a list of things that are more or less comparable to one another. So in the abstraction, you want to be able to do all these things within for a list, right? You want to be able to create it. You want to be able to insert some new item into it. You want to remove stuff. You want to check whether something is in there or not, right? Then in concrete, then we have to talk about how do you instantiate this list. And it goes back to even the first term when you learn things like C programming, for instance. Then at that point of time, I think probably some of the biggest things is that, okay, one is that you learn arrays. And what is an array? Array is a contiguous space in memory. So meaning that we're going to block a certain area within the memory, given addresses, right? And then when you store information, it's going to be stored in consecutive address spaces. That is basically the physical concept of an array. Now, and then there is a linked list. Then you realize that there is a different way of representing information that doesn't depend on their memory addresses. It doesn't have to appear together as long as you have a way to reference one another. This is the concept of pointers. So now, just based on these two concepts, you can then build a lot of other things using these two things as a building block. And we are going to take a look at some of these examples over the coming weeks. Okay, so now we go on from list, and then we are going to create more and more complex structures. So we start to look at other things that look linear, right, like stacks and queues. And then they start to become non-linear. So when we talk about trees and graphs, these are the cases when you have some form of dependencies across the data items. And the dependency could be hierarchical, or it could be a flatter structure, but there is a lot of connectivity involved, which in this case is a graph. Now, beyond defining what the abstract data types are, we need to talk about the different ways we can implement them. What are the distinctions between all these different ways? And what can we do with these data types that allow us to solve ever bigger problems? Okay, now that is going to basically take us to discussions about, are we solving a problem correctly? Then you need to know what is the abstract data type. And because just from that interface, you can already solve problems with the expectation that stack is going to do something, tree is going to do some other thing. But if you really want to solve problems efficiently, then you need to know data structures. And when we talk about data structures, we try as much as possible to develop understanding that gets down to the lowest level possible. Because the higher the understanding you have, or even the physical constraints that you're facing with the devices that you're running it on, and the more likely it is that you're going to be choosing the right data structures and the right implementations to actually solve your problems. Okay, and that's actually part of the reasons why we start this CS with C programming, is so that you develop some sense of the system, that there is some limitation of memory, there is some limitation of the computational processors, and you need to bear these things in mind because it's going to make a difference whether you run your program on a supercomputer or on a Raspberry Pi, or even like different types of computers, right? Okay, so when we talk about abstract data type, we basically talk about the logical form, and we talk about the structures. Most of the time, we really talk about the implementations, the subroutines, and the physical form. Okay. Now, what are applications of data structures? Well, there are a lot of things that we can use it for. Okay, so one of the things that you probably find familiar, okay, shortest paths, right? I mean, you use it a lot. You do Google Maps, and then you are trying to figure out what is the fastest way to go from one place to another place. And that is going to, they need to know where the roads are, or in the case you're taking MRT, then you need to know where the stations are, which stations are connected to one another. Basically, it's a graph representation of the problem, and then you start to run algorithms that can get you the shortest route, right? Document retrieval. So you think about the way that Google solves the problem search. You type in a keyword, and then within milliseconds, you get some answer. Now, Google spends a lot of effort and time to try to get that result as fast as possible to you. And that is not a trivial problem, because there are so many web pages in the world. Identifying which ones are relevant is a problem in itself, and knowing which ones are relevant and then serving it to you within milliseconds is another problem. And when you talk about how to do things in an efficient way, these are exactly the kind of setups that you need to take into account. Can the solution that you devise scale up to really, really large sizes? Because the problems keep getting larger. Okay, now related to document retrieval is natural language processing, right? So you want to understand text. Text, if you talk about text, most people think, okay, text means like a series of words, it's a sequence. But we all know that text is not a sequence, right? Text is actually hierarchical because you can have phrases within a sentence, and the sentence can form compound sentences. And even within a proper sentence, you have different parts of speech that plays different roles. Something is a noun, something else is a verb, something else is the object, noun phrases, and things like that. So when you do NLP, a natural language processing, for instance, then you're going to encounter hierarchical representations of sentences, such as, in this case, we call it parse tree. Okay, and game design. Okay, game design, well, I mean, all of us play games, right? And a lot of times when you play games, you can play against an AI. So for example, like Pac-Man, you move around and you try to eat the stuff and avoiding the monsters, right? And the monsters are moving automatically, right? Well, you might think that they're moving randomly, and probably to some extent they do, but most of the time they possess some level of intelligence, in the sense that sometimes you can avoid them and you actually get affected, like you die because the monster eats you and stuff like that. Now, if you ask about how is it possible that the game designers built in the intelligence within the games, a lot of these things is about anticipating your moves. And the way that they store that is something that is called a game tree. Now, a game tree is a representation of the game states. So for example, let's say if this is your state of the game, and the next state, let's say, is the computer state. Then the computer is going to anticipate if they were, what are the possible actions they can take, and given each possible action, what are the other possible actions that you can take in return. And the difficulty of the game comes down to how far a look ahead you have in terms of anticipating your moves. So if your computer is very fast, they can take a lot of look aheads, right? They can anticipate maybe 10 different moves. And 10 moves deep is actually a very big data, because you have to see for all the possible moves you can do. They're going to anticipate this, and then what else can you do? And that kind of representation is usually represented as a tree, and that is going to allow the game AI to keep track of the game states and to try to devise a move that can beat you. So there are different applications of data structures. So what I thought we could do is just to take a look at one of them. So basically the idea of decoding it is that we're going to follow the tree structure. And of course, we're not showing the tree here because the tree is a little bit big, but the idea is that you have these branches that are go to the left or to the right, and one side is 0, the other side is 1. But you can kind of simulate the tree here because you encounter the first 0 and you realize that there are many zeros, and 0 by itself is not going to give you a letter. So then you try 0, 1, but the same way, there are many 0, 1s, by itself it's not going to give you a letter. And you keep going, and at some point you go 0, 1, 0, 0, but even 0, 1, 0, 0, there are still many of them. So then you need to go to 0, 1, 0, 0, 0, 1, which means that the first one is going to be a W, right? So the same way it's 1, 1, well, 1, 1, there are not that many choices. So by the time you come to 1, 1, 1, that is an E, right? And then you have another W. And in this case, you have 1, 0, 1, 1. 1, 0, 1, 1, this is 1, 0, 1, 1, right? Which is an I. And then in that case, we have 1, 0, 0, 0, and that happens to be an L. So this side is an L, and you have another L here, okay? And then we have 1, 0, 1, 0, and 1, 0, 1, 0 is a H. So in that case, that is a H. And then you have, well, here you have 1, 1, 0, 0, and 1, 1, 0, 0 is an A. Okay, and 0, okay, that is an A, right? 0, 1, 1, 0, 0, 1, 1, 0, well, that itself is not enough, right? Because I have many 0, 1, 1, 0 here. So I need to keep going, 0, 1, 1, 0, 0, 1, 0, that gives me a V. That is pretty long, all right? So then another triple ones. And we have 0, 1, 1, 0. So that's 0, 1, 1, 0. Well, I have a number of them, so I need to go a bit more. But the next two ones are going to give me the F. And then I have 0, 1, 0, 0, 0, 1, 0, 0. There are a few possibilities, but if I consider the next digit, which is 1, then we have a U. And finally, we have the 0, 1, 0, 1, which is an N, right? Now, we notice a few things here. So firstly, we realize that the frequencies are different, right? I mean, the letters are different. Frequencies get different length of code. So things like V is pretty long, right? So it has like 7 bits. Something like E only has 3 bits. And the idea is that the more frequent letters are going to be given fewer bits, because then you can save a lot of bits. Because something is frequent, then you just use a short code. Something is infrequent, you use a long code. And because it happens infrequently, then overall, you're gonna save space because you are spending your bits on the things that actually occur frequently. Now, if we return to some of the concepts that they were describing in the video. So he talks about this being a lossless compression. So lossless means that you lose no information whatsoever. You can recover back the original information that you encode. Now, that is important in certain applications. And in particular, for Huffman code, there is a proof that it's going to basically do that correctly, and it's going to always decode into the original message, and it's going to do that in the shortest possible number of bits. So based on these things, and we begin to see that when we are trying to solve a problem, sometimes the solution depends on how we represent the data that we use to solve the particular problem.